Okay, so today's class is on thermodynamics. Now the first big question with thermodynamics is, why do we care? Because it's a big word, sounds like science, sounds boring. Thermodynamics is really the science of energy in general. So it's a lot bigger than just the idea of the movement of heat, although when you get into the laws of thermodynamics you find out that heat is energy. And you'll see that in our humorous little video that we have to show. But thermodynamics essentially just means the movement of heat, dynamics of heat, moving heat. So let's do this real basic first. So first of all, why does heat move? So let's write that. That's a really big question and one of the most important questions of thermodynamics. Why does heat move? Well, heat moves from a warmer body or a hotter body to a lower temperature or a cooler body. What is temperature? That's another question to ask. What's the relationship between heat and temperature? We'll talk about that a little bit more, but what direction does the heat travel? Does heat travel from cooler to hotter, or does it travel from hotter to cooler?
Yes.
Travels from hotter to cooler. And that's the same thing that we've talked about in previous classes, this idea of the equilibrium of energy, energy seeking its equilibrium. So you have a hotter body of air, water, metal, whatever it is, wants to give up its heat. The heat wants to flow from the hotter to the cooler mass. Okay? So what we're trying to get to is applied thermodynamics, the idea of how do we control the motion of heat? How do we get heat to move from one place to another? Well, the simple answer is to create a temperature condition in which the temperature is cooler in one place than the area that we want to remove heat from, or vice versa. If we want to move heat from one place to another, we want to create a condition where there's a differential in temperature, and that's how we move heat. So simplistically, that's what we're doing. So if I want to move heat out of this room, what do I have to do? I have to create a condition in which the temperature is lower somewhere adjacent to this room. So let's say that we put up a curtain wall right in the center of this room, and somehow using magic I made it 95 here and I made it 55 here. Okay. Well, if I open up the curtain wall, what would happen is this air would mix together and it would seek an equilibrium between those two until they were completely stabilized.
That's the same nature like what water does. It does the same thing.
Yeah, I mean, all matter, it doesn't matter what it is going to seek a thermal equilibrium. And thermal equilibrium is defined by temperature.
Does it do that? Does it seek a room temperature? Is that why the hot moves to cold?
Well, it doesn't. It's not like it's seeking a particular temperature. It's not like it's got something in mind that it wants to get to.
Right.
It's just trying to seek an equilibrium, meaning that it's trying to balance it out. So we're going to talk about the first and second laws of thermodynamics, but there's also what's called the zeroth law of thermodynamics. And that's actually real. It's called the zeroth law of thermodynamics. And the zeroth law of thermodynamics states that if two bodies are thermally equal, meaning that their temperatures are equal, then a third body that's temperature is equal to either of the two is also equal to the other. The concept is, I mean, that's a really simple, obvious thing to say because we're used to dealing with temperature, but it's helping us understand what that actually means. Because really what we do is when we say 75 degrees, that's really just an arbitrary measurement that we apply to a condition that we see, a thermal condition that exists. The scientific concept that we're trying to apply here is that, when we talk about temperature, it's something that we're familiar with. And the danger when you're familiar with something is that you apply certain realities to it that may or may not exist. So we'll say something is, it's 95 degrees, so that's hot to us, or it's 200 degrees, that's hot to us. Well, that it's hot in relation to something that is cooler than it. There is no such thing, kind of getting back to Kyle's question, there is no definition of what warm, cool, cold, hot really is. The only real definition that exists is absolute zero. That's the absolute absence of heat. You get to a point where there is no more heat, and that's the only real solid established thing. There is no ultimate high temperature. It can keep going up. So you say, well, compare the Sahara Desert to the surface of the sun. Well, obviously they're very different, but we would still say the Sahara Desert is hot. So there's these sort of arbitrary things that we apply to the concepts of hot and cold. But what the zeroth law is essentially saying is that when two things are in a state of equilibrium, two things that are adjacent to each other, in contact with each other, that are at a state of equilibrium, meaning no heat is transferred, then you can say that they're the same temperature. So if there's something else that's also at a state of equilibrium where heat's not moving, you can also say that it's the same temperature. So let's say that I didn't own a thermometer and I couldn't, there's no way that I could, but I could somehow prove that this body of water and this body of water, that no heat was transferring between them. I could say absolutely that these two are the same temperature. So that's the zeroth law of thermodynamics. But essentially what we're establishing here is this concept that we're manipulating conditions. When you talk about applied thermodynamics, you're manipulating conditions in order to create conditions in which you have a differential in temperature between different matter, and in order to transfer heat from one to another. You have to have a differential in temperature. Now let's talk about let's ask a bigger question, okay? Because this is another area where we'll apply something based on our experience, but then reality sometimes gets in the way. Let's say that I have a glass of water. So I have this glass. And this glass of water is full of 212 degree water. So it's water that's at the boiling point, okay? And then I have this room that's 74 degrees, okay? Now, which has more heat in it? This room or this 212 degree cup of water?
Probably the room. Because it has more total area. Take more BTUs to cool it down.
It has more total molecular mass. Much more molecular mass in all of the air that exists in this room than in the water that's in this glass. Now, the average molecular energy within this vessel is greater. So the temperature is greater within this vessel. So we say if you average out the molecular energy in here, it's greater than what's in here, but there's still more heat here. So for example, if I immediately instantaneously transfer the heat out of this 212 degree water into this space, how greatly would it affect the temperature of this space? Nominally. Although, you know that if this were 212 degree water, it would be constantly transferring its heat out of this to the space until this water acclimated to the temperature of the room. Is that we can think wrongly about it. We can say something is hotter. And what we mean when we say hotter is we mean it is of a higher temperature. But that does not mean that it has a greater heat content. Does that make sense? And so we're talking a lot about those two different things, and you have to think of them differently. But we can still affect heat transfer one direction or another, not based on the amount of overall heat in those two spaces, but based on the temperature differential between the two. So that's what we have to affect, is the temperature differential, the average molecular energy in that space. And we don't have to worry about how much overall energy there is in the space. Okay, so now let's talk a little bit about the laws of thermodynamics and getting a little bit more specific about what they are and how, the rules that govern how heat moves and the work that heat's done. So first of all, I have a little video for you to watch. Hopefully you'll enjoy it as much as I did, which was immensely. It has puppets in it.
The first law of thermodynamics. Heat is work and work is heat.
Heat is work and work is heat.
Very good. The second law of thermodynamics. Heat cannot of itself pass from one body to a hotter body.
Heat cannot of itself pass from one body to a hotter body.
Heat won't pass from a cooler to a hotter.
Heat won't pass from a cooler to a hotter.
You can try it if you like, but you'd far better not.
You can try it if you like, but you're far better not.
Cause the cold in the cooler will get hotter as a ruler.
Cause the cold in the cooler will get hotter as a ruler.
Because the hotter body's heat will pass to the cooler.
Cause the hotter body's heat will pass to the cooler.
Heat is work and work is heat and work is heat and heat is work. Heat will pass by conduction in the heat
will pass by conduction.
Heat will pass by convection.
Heat will pass by convection.
Heat will pass by radiation.
Heat will pass by radiation.
And that's a physical law. Heat is work and work's a curse. And all the heat in the universe is gonna cool down. Because it can't increase. Then there'll be no more work and there'll be perfect peace.
really?
Yeah, that's entropy, man. And all because of the second law of thermodynamics, which lays down that you can't pass heat from a cooler to a hotter. Try it if you like, you far better.
Cause the cold in the cooler will get hotter as a rule. Cause the hotter body's heater will pass to the cooler. You can't pass heat from a cooler to a hotter. Yep, try it if you like, but you'll only look a fool. Cause the cold in the cooler will get hotter as a rule. That's a physical law.
Oh, I'm hot.
What? That's because you've been working.
Oh, Beatles, nothing.
That's the first and second law of thermodynamics.
Come on, that's pretty good stuff. So, first law of thermodynamics, second law of thermodynamics. First law of thermodynamics basically says that create energy. All the energy that exists in the universe is what it is. You know, there's a set amount of energy within the universe, and that is measured by heat. We measure everything. We can measure everything by heat. You can convert watts to BTUs. You can convert any measure of work, horsepower to watts, watts to BTUs, and it all is tied back to the transfer of heat energy. We can measure it in that way. And then the second law of thermodynamics is the idea of entropy, that you can take heat and you can take energy and it can be transferred from a usable to a more unusable state, because everything tends towards equalization. And we can use the illustration of, once you have some ice in this room, and once the room transfers its heat into that ice and the ice melts, well, now the energy transfer is done. The energy's still there, but it's no longer usable. So now we have to do something in order to create a differential in order to cause energy to move again. So from a philosophical standpoint, the energy's still there. It's just equalized in how we can't do anything with it anymore. The second law of thermodynamics covers that idea, and the term entropy is the term that they use for the transfer or the conversion of energy from a usable to an unusable state. And a more simplistic way that people will explain entropy is they'll say things tend towards disorder, which is not an exactly perfect way of explaining that, but it's a way that sometimes we can think about it, in that we use things up. We take the power plant and we create energy, and then the energy runs through our circuits, and then it becomes in this unusable state. It isn't necessarily a disorderly state, but it is a state in which it's not doing anything for us anymore. It's just sort of at rest now, because it's achieved its equilibrium. So most of the energy that we see on Earth comes from the sun. We have a little bit from the stars and things, but the bulk of the energy that we have on Earth is injected into our system constantly by the sun. And so we don't have a closed system here. If we had a closed system here, where we had just the energy that the sun gave us and the sun went out, how long would we last? Not very long, and that's because we constantly have that differential that's being provided us by the sun. Once we no longer have that, then all we have is our stored resources that the sun's provided us in the past, like oil or whatever, in order to continue to go on. But as we know, that wouldn't last very long. All right, so now let's talk specifically about ways that we create conditions in which we can move heat from one place to another. Let's first talk about change of state, or what we call latent heat versus sensible heat. So first, let's define what sensible heat is. Sensible heat is if I create a change in temperature and I see it change on the thermometer. That's pretty obvious. Sensible heat. Okay. Now, are there ways in which you can actually move heat, but you don't see any change on a thermometer? Let's say I've got a big pot of water here, and I put a flame under it, and that water quickly I'll be able to put a thermometer in, and I'll watch the temperature of that water rise. Let's say it starts at 75 degrees, Kyle, and the temperature of that water is just going to keep rising, and then it's going to hit a point, and it's going to stop rising. At what temperature is it going to hit that point at sea level?
Boiling point. Oh.
Boiling point, 212. It's going to hit 212, and then the temperature is going to stop rising. Well, what's happening?
Equalizer is the flame.
Well, it's doing that anyway, because that's what it's doing. It's absorbing and it's trying to create equilibrium with the flame, but it's increasing the temperature of the water continuously. But it hits 212, and then it stops increasing in temperature. Why is that? Well, it's because within a molecule, okay, you have all these different atoms that bond together in order to create these stable forms that we see. We see water, we see, what we commonly would call air. But there's these stable forms in which, water isn't just one thing. Water is H2O. So we have hydrogen and we have oxygen in water in order to make it. So it's not just pure oxygen, it's not just pure hydrogen. It bonds together and creates this molecular form that we know as water. Well, what happens is all these water molecules are all bound together in this form that we call liquid. Well, once it gets to a certain temperature, those bonds start to break down because it's reached a point of molecular excitement, meaning that these molecules are starting to move as you increase. In fact, when we talk about temperature, really what we're talking about is molecular velocity. We're talking about how fast are these molecules moving within, what is the average molecular velocity within this container. So as the temperature of that pot of water is increasing, those little molecules are bouncing faster and faster and faster against each other. Well, eventually you hit a point where they stop bouncing faster and they start breaking apart from each other. They start breaking the bonds that they normally had that we would call liquid. What we perceive all of these thousands and millions of molecules together. We perceive that in a way and we say that's liquid because of the way that it looks and the way that they bind together. Well, eventually that breaks and they start to create steam. Okay? Well, they don't get hotter again until if you were able to recapture that steam and keep heating it, then it could get hotter. But as long as it's in that change of state form, as long as it's actually in the process of boiling, it can't be hotter than 212 at atmospheric pressure, right?
Well, correct.
In actuality, there's a lot more heat transferred to take that water and take it and make it 212 degree water to 212 degree steam than there was to take that water and take it from 75 degree water to 212 degree water. And that's really the magic in air conditioning. That's the magic that we deal with in air conditioning and refrigeration, is the fact that what we're used to seeing in everyday life is the heat that goes into raising and dropping the temperature of things. But there's so much more heat transferred in the changing of things from one state to another state. And really everything can be changed from one state to another. You can take air and you can create liquid air. You can take nitrogen, you can create liquid nitrogen. But it just requires conditions that we don't normally see in our environment. We think of water as being liquid, but in reality, water can exist in all three states. Water can exist in ice, which is a solid state. It can exist in liquid. Again, it can exist in vapor, which is what we would call steam. But all of those transformations involve a lot more heat being moved than the actual temperature change. Because you can have ice, you can get ice to 32, and then you can continue to cool ice once it's fully solid. But if it's in the change of state, it takes a lot more energy to take 32 degree water and change it to 32 degree ice than it does to take 32 degree ice and change it to 20 degree ice. Does that make sense? You guys with me here? Okay. All right. So in the compression refrigeration circuit, I don't know how well you guys can see this, but we're actually, the way they do it is they kind of take this little blob here and you kind of watch it travel through the circuit, and it sort of shows you what happens here. It's compressed to a high pressure gas. It goes through the condenser because now it's a very high pressure, high temperature gas, and that heat is now transferred out of the condenser into the air around it. It cools down into a liquid. It hits an expansion valve, which is basically just a metering device that instantaneously drops the pressure, causes it to expand into a mixture between liquid and vapor, and it starts to now absorb heat out of the air around. Goes back in. What we're working with here is we're working with two principles. We're working with the principle of altering the temperature of something in order to create a situation where heat wants to move. And we're using this secret sauce of latent heat transfer in order to actually change something from one state to another state, which is even more powerful when it comes to getting heat to move. So you have to have the temperature differential. That's what we learned. You can't move heat from a lower temperature body to a hotter temperature body. That's what the little song taught us. You can't do it. You can't move heat from there to there. You have to move heat from the hotter body to the cooler body. So we have to create a temperature differential in order to move the heat the way we want. When you're cooling a room, say we want to drop the temperature of this room, we want to cool this room. So what do we have to do in order to get heat out of this room?
We have to create something better.
We have to create something colder in order to transfer heat out of the room into the colder body. Now, if I took, let's just say I had another room that was a little bit cooler than this room and I connected them together with a duct. Would that create equilibrium? Yeah, it would, but it still isn't. It wouldn't be very much. You know, if I took another room that was the same size, that was a couple degrees cooler, I could transfer some heat out of this room, but it would just create an equilibrium between the two. It wouldn't be significant.
And you would have to keep on adding rooms in order to keep that change up.
Correct. And what we need to be able to do is create a system in which we can create a high temperature where we want a high temperature and a low temperature where we want a low temperature, and continuously move that heat where we want it to move.
So that when it's in the high.
Let's say you have a condenser that sits outside, all right, when it's running in cool mode, and you see that hot air. You've ever thrown your hand over a condenser, you see hot air coming out of that condenser. Well, you can think of it in two different ways. You can think that, well, I'm cooling off the condenser, okay? But a better way of thinking of it is I'm actually heating up the outside air, because the refrigerant gas that's inside that condenser coil is hotter than the air outside of it. So the heat is going out of that condenser coil into the air around it. So we're transferring that heat out. Now it's going back around, so it's cooling off, it's becoming in a more stable state, it's kind of settles itself down into a liquid. That's kind of a way that I like to think of it, you know, when you're talking about change of state. Think of it like, okay, let's say that this room was full of ping pong balls, okay? Think of and the ping pong balls are the molecules. And they're all kind of bouncing slowly. You just kind of vision that. They're all just sort of bouncing around the room. Now what happens if I take this wall and I start to move it this way? What starts happening? They just start bouncing more and more and more and more, right? And if I brought it all the way to here, so there was just this tiny little bit of space, those things would just be going mad. They would just be bouncing all over the place. Well, if you think of temperature as the average molecular velocity, meaning the average speed of the ping pong balls, well, when this is all the way to the wall here, sorry Travis, the average speed of the ping pong balls is extremely high, therefore the temperature is high, okay? And so now we allow those ping pong balls that are going really fast, now they're heading into the condenser, they have this really high thermal energy, and now we start to allow the heat to go out of those ping pong balls into the space around it. Now what do they start to do? Because now they're settling down, and they start to calm down again, and they actually calm down into a liquid state, okay? Then they hit this expansion valve here, and now we're restricting them. We're only allowing a few ping pong balls to go through at a time, okay? And now they immediately break their bonds again because we've released them from that pressure that was still holding them together. Because essentially what we're saying is we have two things that are happening at once in this circuit. You have the fact that we're continuously compressing and depressurizing, and we have the fact that of the actual temperature of the object. So let's think of it this way. Let's say that we had I asked the boys this question the other day. Let's say that you were boiling water and you were trying to cook potatoes up in the mountains. Does the water boil up in the mountains at a higher temperature, or does it boil at a lower temperature?
Well, it's at a lower temperature.
And why is that?
Lower pressure, a lower atmospheric pressure.
Okay, so in the terms that I've been describing,
there's lower mass per unit of volume. Meaning there's lower thermal energy per unit of volume.
Sure, and thinking of it in a more simplistic, infantile way, which is how I like to do it. If you have less force holding something together, because atmospheric pressure is pressing in on all of us all the time. It's kind of holding us together, and even with the water, it's pushing it together, meaning it's kind of forcing it into a artificial liquid state, if you will. Now, if you start to release those bonds, now those molecules start to be allowed to move away from each other, even with just the atmospheric pressure. Therefore, it takes less heat, less temperature in order for them to break their bonds because they have less pressure to begin with in the mountains. Now, opposite, put a pressure cooker on it. You take that pressure cooker, and as that water starts to boil, it's actually creating pressure within that vessel. Now, does the water boil at a hotter temperature or a colder temperature?
Much hotter temperature.
Much hotter temperature. Why? Because you have this pressure that's now forcing it together. As it boils, it's creating more and more pressure, and it's forcing those bonds together. And so it allows it to get hotter and hotter and hotter as the pressure increases, because that pressure is keeping it from expanding into a vapor. You follow what I'm saying? So as the vapor fills up that space and creates more pressure, it's forcing it together even more, and it's kind of that compounding effect.
So compressor create heat?
It's concentrating the heat.
That concentrating the heat's a very good way of looking at it. Now, there's the compressor.
Not necessarily. All right. Oh, let's go ahead.
No, it's a good question. Let me go ahead and put this up here again.
Because if it can get it, if it can make whatever you're doing hotter, then it actually like create it as well.
Okay, sure. Let's talk about this. Let me draw a terrible picture of a compressor again, like I did last time. And we're gonna have this is our discharge line, so this is the line coming out. Okay, this is our suction line, this is the line coming in. Okay. Now, those of you guys who know air conditioning, is that which one's smaller?
The liquid part. Discharge.
The discharge line is smaller. And then this one here is larger. So by its very nature, we're trying to keep it compact on the high pressure side, and we're trying to give it more volume on the low pressure side. If you're thinking about it just kind of simplistically, okay? So what's happening? What's actually occurring inside this compressor? What is actually happening? Because there's no magic. Basically, down here we've got a rotor that spins around and it runs a shaft, and this shaft's, we'll just draw this as a scroll compressor, okay? In a scroll compressor, all that it's doing is it's creating oscillating motion in order to create smaller and smaller compression chambers. So you've got these two plates that fit together, and they kind of just do this. And as it actually is drawing in the refrigerant and creating these smaller and smaller chambers until it compresses it, and then it ejects it out through the center of the scroll. So essentially, it's just larger volume to lower volume. Now, how's it adding heat in that process? Well, there is some heat added because this is a motor, and motors generate heat just through their operation. So there is heat added when the suction gas comes down and it is warmed up by the actual compressor windings and by the body of the compressor. You run a compressor, it's hot even if it's not pumping. And if you've ever seen a compressor that's not pumping, you still touch it, it's still hot because it's still a motor. Okay, but what's really getting hot, what's really causing the bulk of the heat within a compressor, is not that you're actually adding heat to it at all. It's that you're taking, it's the idea of this room. You're taking this refrigerant that's very loosely bound, it's in a vapor, and you're taking it and you're slamming it together all at once, okay? Now, you would say, okay, if I take all this vapor and I slam it together all at once, why doesn't it become a liquid? This is a thing that I kind of had in my head for a long time when I was in AC school. Why doesn't it just become a liquid when you slam it together all at once? Well, because it's directly proportional, meaning that the more that you slam it together, the hotter it gets. But it also has greater bonds against it, but the hotter it gets, and it has greater bonds, but the hotter it gets. So it can't become a liquid until you actually allow some of that heat to transfer out of it, and then it can settle down into a liquid. So the heat content of the refrigerant hasn't changed at all when you compress it. Key point here: the heat content of the refrigerant has not changed at all when you compress it. The instant that it's compressed, it has the exact same heat content that it had before it was compressed. But what's different? The temperature is different. The average molecular velocity is different. Okay? And that's what we've just done. We just pulled the trick of taking something that it has the same amount of heat in it that it had before, but now creating a giant temperature differential. And so that's how we do this trick of making something hot so that it can become cold. But that's perception, because we haven't actually changed the amount of heat in it at all. We've just created a hotter body so that we can now cool it. We've taken this heat that we've absorbed through the evaporator coil out of the house. And now, because it's in this loose state, that we've allowed it to kind of exist where it's boiling off and it's loosening its bounds and it's absorbing heat. And now we get it in that compressor and we go whammo, and now all of a sudden the temperature shoots way up. Now we can get that heat back out of it. Does that make sense? And that all that heat rejection in an air conditioning system happens in the condenser coil from what we would consider to be already hot, because we go outside and say, oh, it's hot. It's 95 degrees outside. How could you reject heat to this temperature? Well, that's the trick of compression refrigeration and latent heat transfer. Because not only are we transferring from hotter to colder, but we're changing state in the meantime, which allows us to compact a bunch of heat into a couple pounds of refrigerant. See, that's what's amazing. In an air conditioning system, we're taking anywhere from 2 to 15 pounds of refrigerant in a regular residential system, and we're cooling an entire house with that. We're rejecting all the heat that it comes from a house through this medium of a couple pounds. But the secret sauce is that we're constantly changing the state of it, and that's where all that heat is really transferred in that latent phase, where you're not actually even seeing the thermometer change. We're not talking about subcool and superheat in this class or saturation or any of those types of things, but you guys are technicians. As you're doing that, that's what you're seeing. That's what you're watching occur when you see this saturated state. You're seeing heat transferred in latent. Your heat transferred when a medium, in this case being refrigerant, is actually changing its state from one form to another form. Of the constant transition of it breaking its bonds in evaporation or boiling, as we call it, and then condensing, which is it settling back down into that more compact state again. Does that make sense? Jason, does that answer your question a little bit?
It does.
So, another quick reiteration. Oh, if you don't take away anything else, those of you who actually fix air conditioners, if you don't take away anything else other than understanding that a compressor doesn't actually heat anything other than just the fact that there is some heat that goes into in a mechanical process, but that it is compressing and exposing temperature, that helps you understand a lot of things. And if you start to think about it in terms of, okay, why do I have high head pressure? Thinking of all these different things, you can start to make a little bit more sense of that. And then the perception, I've had customers ask questions like, well, how does this even work? I mean, in the way of the way a heat pump works in heat mode, the people will ask a lot. I mean, how are you getting heat out of it? It's 25 degrees outside. How are you going to get any heat out of that air? There's no heat in that air. It's cold outside. Well, there's a lot of heat in that air. There's actually very little difference between the heat content, overall heat content of 25 degree air and 75 degree air, 80 degree air, 90 degree air. Because as you know, when heat really, it gets to minus 460 or whatever it is before the heat is really all used up in any matter. You're actually approaching absolute zero before the heat content is zero. So while there is less heat content, there's still plenty of heat in that air outside, even when it's 25 degrees. And by using this manipulation process, that's how we can force the heat to move where we want it to move. So that's thermodynamics, the movement of heat. Any questions about any of that?
I don't think so.
All right. Well, thank you guys for your